So we'll continue now with the ray diagrams, but this time now we are going to talk about refraction of light and solve a couple of problems. Okay, so here we have an important diagram, characteristic of the refraction of light. Now, what is the refraction of light? We know that we say that light travels in straight lines, which we show with, we represent with rays, light rays. But the light travels in straight lines when it travels in the same medium, like in air or in vacuum or in water. It travels in straight lines, true. But occasionally the light from one medium can move on to go onto another medium, to transmit in a different medium. For example, when light travels from air into water, which is a very common transition, or from air into glass, like to come inside our homes through a glass. So when light moves from one medium to another, then it changes direction. And the reason for that is because it changes speed. It travels with different speeds in the different media. So here we have this example. I'm not going to go into details, just to remind us so that we can solve a problem. Here, for example, we have air. Say this is air, and there is a light ray that comes through the air and strikes here a different medium, the boundary between air and water. So here, the second medium is water, the first medium is air. So you see, while the light travels in the air, it travels in straight lines. But once it meets the boundary with a second medium, it bends. And it travels after the boundary, though. Look at this, it continues traveling in a straight line, but now it travels in a different direction. So it bends. So this bending of light is this phenomenon actually that we see is what we call refraction. So refraction is actually the bending of light. Refraction is the bending, is this phenomenon actually, is the phenomenon where we see the light bending, is the bending of light when it meets a different medium, bending of light. And this bending is due to the fact that it travels at a different speed inside the second medium. So the phenomenon is the bending, which is the refraction, and the cause of this refraction is the travel at a different speed in the second medium. Now, the question is, okay, it bends, fine, but does it bend toward the normal or away from the normal? It's always the normal when we talk about a light ray striking a boundary or a surface. So the normal again, once again, we have to draw the normal where the beam of light meets the boundary. And now to decide whether it bends towards or away from the normal after it enters the second medium, it has to do with refractive indices of the two media. I don't know if you have been so far away in the book, which is chapter 13, I think, to know what the refractive index is, but we assume that you have, because we need to discuss the important aspects of this chapter. So the refractive index, of a medium, is actually the ratio between the speed of light in vacuum to the speed of light in the medium that we are talking about. In air, for example, this index of refraction would be characteristic of air. And this speed here is the speed in which the light travels in air, okay? And of course, this is the speed of light in vacuum, which is a constant. It's a constant, it has a specific value, a very important value, the speed of light in vacuum, which is, what is this, 3 × 10⁸ meters per second. We take it as constant, it's a universal constant. So but in air, now light in air travels practically at the same speed as in vacuum. So for air, this is equal to 1 because we take that this speed is practically equal to this one. It's very nearly the same for all practical purposes. So fortunately, the index of refraction of light in air, we take it 1 as much as it is in vacuum. Okay, so but for any other medium like water or glass or different types of glass or perspex or whatever other things are transparent. Of course, the media have to be transparent to allow light to travel in. For any other transparent medium, the index of refraction of other media is more than 1. Okay, so the indices of refraction are given in tables, so there's no need to worry. I mean, they will be given to us unless if this is the unknown in the problem and we're asked to find the index of refraction. In water, the index of refraction in water is 1,33 and so on. But that's a common index of refraction that we meet quite often. Anyway, I mean, you don't have to remember this by heart, of course. But you do need to remember that the index of refraction of air, you can take it as 1. And in fact, we can give it more significant figures, like 1,00. All right. Okay, so let's go back to our problem here. Now, whether the ray, the incident ray, once it meets the boundary and bends, whether it bends away or towards the normal depends on how those indices of refraction of the two media compare. If as in this case, the index of, if the first medium 1, which is the air here, is optically less dense than the second medium, then the light ray will bend towards the normal. As it's shown in this example, air is a less dense medium than water, and the water is the more dense. And when we say dense now, we don't mean like dense, that the density of objects that hold it more dense. It's not like the density that we say mass per unit volume. This is a optically dense. It's a different concept. Less dense medium, optically less dense medium is a medium where light travels at a bigger speed, and the more dense, optically dense again, medium is where light travels at a slower speed, finds it harder to travel. So be careful now what we mean by optically less dense and optically more dense medium. So from less to more dense medium, the ray will bend towards the normal, which means if you compare this angle, which is the angle of incidence, and this, which we call now the angle of refraction, not reflection, be careful, refraction. Now, the angle of refraction is smaller than the angle of incidence because this ray has bent closer to the normal, towards the normal. And once again, we must be careful that the incident ray and the refracted ray and the normal all belong to the same plane. They are part of the same plane, like the plane of this page here. Now, of course, the opposite happens if light moves from a medium which is more dense to a medium which is less dense, which could be the opposite of the top diagram. Now, for example, now we can have light moving from water. This is the water again, and this is the air. Now, if light moves from water out into the air, now again there will be refraction because again the light will bend, but this time now it will bend away from the normal. So here is the normal, here is the incident ray, remember, from water out into the air. For example, somebody might be at the bottom of a pool and shines a torch, something, I don't know, a torch towards the surface of the water. Here there is a torch. So light in this case falls from within the water meets the boundary between the two media and then bends away from the normal. And in this case now, this is the incident ray, and this is the angle of incidence, theta 1. And this is the refracted ray that has moved away from the normal, and therefore this refracted angle, the angle of refraction, is bigger than the angle of incidence, because light moved from an optically more dense medium to an optically less dense medium. So in this case, we have the light bending away from the normal. So in both cases, we see the phenomenon of refraction. In both cases, we see refraction of light. And in both cases, we see that, be careful now, the refraction happens at the boundary. And when we say boundary, what is the boundary? The boundary is this line, the interface between the two media. So refraction happens at the boundary. But after the light passes to the second medium, it continues in a straight path as usual, because, say, light travels in straight paths. Now, there is a law that we can use to tell us by how much the light refracts away or towards the normal. The law that we call Snell's law, and we're going to take it straight away as given, so which says that here is Snell's law. So you see the first part, I write it in this form, Snell's law, because it's easier to remember. The one side of the equation, you see it's an equation, one side concerns the medium one of the two media. The other side concerns medium 2, the other medium, where the light enters. So say in this first example, the top diagram, the medium 1 is the air here. This will be medium 1, medium 2. So in the first, on the left-hand side, we have the index of refraction of medium 1 and 1 times the sine of the angle theta 1. Theta 1 is the angle of incidence. So this is the angle of incidence. And on the other hand side of the equation, on the right, we have the particulars of medium 2. So we have the index of refraction of the second medium times the sine of the angle theta 2, which is the angle of the light that it forms with the second medium, which is actually the angle of refraction. So this is the angle of refraction. So when we apply Snell's law, you see we have one index of refraction, one angle of incidence, a second angle of a second index of refraction, and the second angle here, which is an angle of refraction. We have actually four variables, 1, 2, 3, 4. If we know 3 out of these 4 variables, we can find the fourth. So therefore, we can use Snell's law in problems to find out whether unknown indices of refraction or unknown angles, whether incidence or refraction angles. Okay, so up to now, guys, do you understand this introduction so that we can look at the problem maybe? And I hope you have, some of you at least, have managed to arrive at chapter 13 in the book, where it's about light. So if you need any question, please send me a message and we can deal with it. And now let us try and understand. Actually, let's do a problem. Not this one, not this one. Let's do this problem first, which looks big and serious, but it's not actually, it's quite easy. Okay, let us see this problem, which we have like, you see this is a piece of some type of glass, they call it crown glass. It's a famous glass. Okay, so light traveling in air strikes a flat piece of crown glass at an angle of 42 degrees, as shown in the diagram. If the index of refraction of crown glass is 1,52, determine etc. Now let's see, first of all, to understand. Be careful, we have to make drawings here always. So if the problem does not give a drawing, a diagram of some sort, we must draw it ourselves. Remember, in physics, we need drawings. We don't do anything without a drawing. So here we have this piece of crown glass, and here is the ray of light that strikes the crown glass at an angle of 42 degrees. Obviously, then this is an angle of incidence. And this is the air. So the light comes from the air and strikes, this is the crown glass. So let's call this will be medium 1, and this is medium 2. This is air, this is glass. Okay. So they give us the index of refraction of crown glass. And obviously, it's an optically denser medium than air. Now, determine the angle of refraction of the light ray upon entering the crown glass, the angle of refraction upon entering the crown glass, which is this one. This is the angle of refraction upon entering. It means here, when light meets the first boundary 1. So find this angle of refraction, okay? And then the angle θ2 at which the ray emerges from the crown glass, that is after boundary 2. And this θ2 we need to find. All right. Okay. So let's start with the question A first. We have the angle of, we need to find the angle of refraction upon entering the crown glass. That means here is the incident ray and here is the refracted ray upon entering. So this is about boundary 1. We forget the bottom part. We just deal now with boundary 1. And we need to find the angle of refraction. Okay, so θ2. We need to find θ2. Ignore all that now, okay? So we deal with boundary 1, and of course, we start with Snell's law. We apply Snell's law for boundary 1, okay? All right, so remember, let's write it N1, the sine of θ1 generally is N2 sine of θ2. Now let us make sure that we understand what is N1, what is 1, and what is 2 in this scenario. So N1 is obviously the particulars of the medium where the light enters the second medium. Okay, so this obviously refers here to the air. So N1 is the index of refraction of air, and the sine of the angle θ1 is obviously the angle of incidence, which is 42 degrees, and we know it, it's given. Now, what is N2? It's the particulars of the second medium now. So the second medium is this crown glass. The N1 is N2 is the index of refraction of this glass, which is 152. It's given, and θ2 is this in the angle of refraction, and this is what this is our unknown. So this angle is our unknown, but we know N1, we know θ1, we know N2, so we know 3 out of the 4 variables here. We can find the angle of θ2. So let us solve for the sine of the angle θ2 first. So sine of the angle θ2 is N1 times the sine of the θ1 divided by N2. In other words, I solved for sine θ2. And okay, let's see. Sorry. Not the time to lose your voice, isn't it? Okay, so sine θ2 now, what is this now? N1 is the index of refraction of air. You remember, which we take as 1. The index of refraction of air, this is 1. We can use even significant figures if we want. Okay, so this is 1. The N1 is 1,0. The sine, now the sine of θ1 is the sine of the angle of 42 degrees. That's given. And N2 is the index of refraction of a crown glass, which is 152, isn't it? I think it was 152. Yeah, okay. So you see, we know all that. We can do the calculations. And what do I find here? I find 0,4402. Okay, too many figures there, but nevertheless. So that is the sine of the angle theta 2. Okay, so now we use our calculator to find the angle theta 2. In this case, if the sine of the angle is 0,4402, then the angle is 26,1 degrees, according to my calculations in degrees. Eh? Okay, so this is the angle theta 2. All right. Now we found this. This is, in other words, our answer to the first question. Find the angle of refraction of the light upon entering the crown glass, boundary 1. So let's make this a bit smaller so that we have more space. Okay. Now, so this is the answer to question number A. Now B, find the angle theta 2 at which the ray emerges from the crown glass. So now we need to find the second angle here after it emerges. All right. Okay, so once again, after we we're going now to apply Snell's law for this boundary 2, right? So now for boundary 2, let's write again Snell's law in general. N1 sine theta 1 equals N2 sine theta 2. Now we need to make sure that we understand what are these 1 and 2 now. Now we're talking about our first boundary is actually now the crown glass. So this is our boundary 1 now, and this will be not boundary, the medium 1, and this will be our medium 2 as applied in this second case now. We forget now the previous one. Now, so N1, in other words, is the index of refraction of the crown glass, which is 1,52. We are referring to the crown glass now because our first medium is, this is now the incident ray for boundary, for boundary 2 now, this is our incident ray and this is our refracted ray, the one that comes out in the air again. So this is our boundary, the medium 1 and this is the medium 2. So this refer to crown glass and this concern the air, which is the second medium. So this is the index of refraction of air, which is 1. And now we have to find the angle theta 2. All right, so we need to find this angle theta 2. But do we know this angle theta 1? Do we know this angle theta 1? Well, if we look carefully at our diagram, from the geometry of the diagram, we do know it because this theta 1, which is now the angle of incidence for the second boundary, this is incidence, and this is the angle of refraction at the second boundary. Now, this angle of incidence is actually equal to this angle here, the angle of refraction from the first boundary. Why? Because you see, this is the normal to the boundary, to the first boundary, and this is the normal to the second boundary. And the normal lines are actually perpendicular to the boundaries, isn't it? These lines are perpendicular to this interface between the two media, the boundaries. So since these are perpendicular and since this is a rectangular block, these lines are parallel to one another. We have, in other words, two parallel lines, which are the two normals. And this ray here, this ray that intersects both of them, what am I doing here? Yeah, so this is the angle theta 2 from the refracted angle from the first boundary, and this here, which is the theta 1, which is the incidence angle at the second boundary. These two angles are equal from the geometry, isn't it? when you have to, I hope you know this from geometry. I hope you learn it geometry, okay? So these two angles are exactly equal, right? And so we know this angle here that we have called now theta 1. We know this angle here. This is 26,1 degrees. We know this. So if this is 26,1 degrees, this is also 26,1 degrees. Okay. So we know 3 out of the 4 parameters here. We can calculate the unknown angle theta 2. But first, let's solve for sine theta 2 again. So sine of the angle theta 2 is equal to n1 times sine of the angle theta 1, referring to the second boundary, yeah, divide by n2. Now this n2 is the air, yeah. So the n2 is 1, the n1 is 1,52, and the sine of theta 1 is actually the sine of 26,1 degrees, which was so much, which was 0,44, okay, 0.2. Right. So if we do here the calculations, what do we find? Sine theta 2, let me see, do I have that? I have no idea what it is. All right. So where can I continue? Let's continue there. From there, if we solve again for the angle theta 2, what are we going to find? That this theta 2 is 42 degrees. Okay, 42 degrees. And look at this angle that we found. We found that this theta 2 is 42 degrees, which is the same as this angle here at the beginning of the travel of the light. The incidence, the angle of incidence at boundary 1. We found that this angle is equal to the angle in which the light emerges from the crown glass. And this is quite a remarkable and interesting and expected actually result. And but why is it particularly interesting? Because it tells us that the incident ray here at the beginning, when the light first met this rectangular block of glass and hit it at a certain angle of 42 degrees, the angle at which it emerges is exactly the same angle. So if we compare the initial incident ray and the final ray as it emerges, these two are actually in the same direction. It's just the second, this ray here is a little bit displaced to the right. I mean, the incidence is like that, and then the angle of the light as it emerges, it's in the same direction, but it's a little bit displaced to one side, to the right in our diagram. And that is why when we look at objects which are at the other side of a window, even if it's a very thick window, like sometimes in the banks they have thick windows, bulletproof stuff. I mean, what we see on the other side, it looks normal, it doesn't look distorted, but it's a little bit, it has the image that we see on the other side, it's a little bit displaced to the left or to the right, depending on which angle we are looking at. But the images that we see on the other side are not distorted, simply because the direction of the light has not really changed. It's just, it has been displaced a bit to one side. So the image is not distorted, it's just displaced a little bit.